Hello there. We are going to do the SN1 reaction of 2-methyl-2-butanol to synthesize 2-chloro-2-methylbutane following this substitution chemical reaction. Here is the mechanism which is explained in detail in your online notes. Since this is a SN1 mechanism, a carbocation will form which will rearrange to the most stable carbocation possible and generate the substituted chloro product. I have already prepared the starting materials and recorded their respective amounts directly in my notebook. According to the procedure, we have to take 2 ml of butanol and 5 ml of concentrated hydrochloric acid. Since these are your starting materials, you have to record the exact amounts. Make sure you read up to 1/100th of the value because we are using a 10 ml measuring cylinder. So here, in a clean 50 ml Erlenmeyer flask, we will place our pre-measured butanol, the 2-methyl-2-butanol. To this, we will add concentrated HCl. Now remember to handle HCl under the fume hood because it is very corrosive. Before you add to the flask, be careful to add HCl in several small portions. So here I am adding HCl in small portions and swirling after each addition. The fumes you will see are because of concentrated HCl. I will add a few more portions, and after I've added all the HCl, I will swirl this reaction mixture for an additional 5 minutes. After these additional 5 minutes, you will observe the formation of another layer in the flask during the reaction because 2-chloro-2-methylbutane has very low solubility in water, creating a new organic layer. We will now pour this mixture in the separatory funnel. Make sure your separatory funnel is closed and has a beaker or any other apparatus under it to catch the contents. After I have poured all the mixture from flask, I will see 2 layers, 2 separate distinct layers. The bottom layer is the aqueous layer while the top layer is the organic layer. See your manual notes to find which is which. Here I am draining out the bottom layer, the aqueous layer that is, carefully out in the beaker. Do not worry if you are not able to drain all the aqueous layer out. Just try to get most of it out. As part of the workup, we also have to add approximately 2 ml of saturated sodium bicarbonate. It is not necessary to read this volume exactly. As soon as we add this, you will see rapid formation of effervescence. This is neutralizing the excess leftover concentrated HCl. The carbonic acid further dissociates into carbon dioxide gas, which is visible as the effervescence. Make sure you do not use the stopper and gently swirl the funnel to mix well. Once the layers separate, we will drain off the aqueous layer into the same beaker we had used earlier. As you can see, the layers have separated. To this organic layer, we will now add approximately 2 ml of saturated sodium chloride. Again, this is not one of the starting materials. We do not need to record the exact amount. Again, just swirl the solution in this funnel to mix well. Sodium chloride decreases the amount of organic product dissolved in the water. Once the layers separate, we will drain off the aqueous layer into the same beaker again. Now the organic layer is left, which I'm going to collect in a dry and clean 10 ml Erlenmeyer flask. If you compare, this is smaller than the 50 ml flask we were using earlier. So I have collected the organic layer in the 10 ml Erlenmeyer flask, and as you can see, as I tilt this flask, there is a smaller layer at the bottom, which is the water layer. I will pipette this bottom layer out, and if you see in my pipette also, there are two separate layers. I will dispose the bottom aqueous layer in the same beaker, and I'm going to put the organic liquid in my flask. I will add sodium sulfate anhydrous to absorb the leftover water. I have let this sit and dry for almost 5 minutes now, and I added just until some sodium sulfate particles remained free flowing like sand. So here I am taking a clean pipette and a pre-weighed clean empty shell vial. I will transfer the dry organic liquid layer to this pre-weighed vial. Make sure to leave the solid sodium sulfate behind. So here is my final product. I will record the weight of this vial with the organic material in it, and I will also record the appearance. We will be calculating the percentage yield of this product using this information. To two separate clean shell vials, I will add approximately 1 milliliter of 0.1 molar aqueous silver nitrate. This is for the qualitative product analysis. For one, we will be testing the starting butanol, and for the other, we will be testing the organic product we synthesized. I'm adding about 4 drops of our chloro product to the AgNO3 solution, and when I will shake it, I clearly see the formation of a cloudy solution in this mixture. Remember to avoid skin contact with silver nitrate because it becomes reduced and turns black-brown. Now for comparison, I'm adding about 4 drops of our starting butanol to this other vial of AgNO3 solution, and on shaking it, I do not visually see any changes to this solution mixture. So if we compare both of them by placing them next to each other, we clearly see the difference. The silver halide formed is insoluble in water and appears as a white cloud or a white precipitate. So if you look at the chemical equation, whenever silver nitrate is reacted with any unknown material and a white precipitate forms, we can estimate that the unknown material must have contained a halide. We will also be doing the IR of this neat chloro product, and we'll compare it with the starting butanol's IR. For the waste disposal, we will dispose of the silver nitrate solutions in the aqueous silver waste container. We will place the organic product, which is the substituted chloro product, in the halogenated organic liquid waste container. The aqueous waste can go down the drain. And once you are done, you will discard the used shell vials and pipettes in the broken glass container.